Okay, so in this video, what I'd like to do is use MATLAB just to sort of show you some examples that help think about what is meant by a partial derivative. So to do that, I'm going to first create a mesh grid. So I'll just make a grid that goes from -10 to 10. So here you can see that the y columns go from -10 to 10, and x, each row goes from -10 to 10. So I've just set up that plane, that xy plane that goes from -10 to 10, and I'm going to define a potential on that plane. So let's actually start with the potential we actually talked about in the last video. So we'll make the potential be x times y. And you can see I've now got this matrix of what the potential is. So each value in this matrix corresponds to an x value and a y value in the respective matrices. And I could look at what a surface plot looks like of that. So let's do surf of x comma y comma v and take a look at that plot. So here, this is what that function looks like. So I've got v on the x-axis. So let's make z label be v. I suppose I should type that correctly, and we'll make the x label be x, and the y label be y, just so we can kind of make sure we're looking at the right things here. So you can see here that the potential is going up, right? Here's the x-axis, here's the y-axis, and if I rotate this from the top down, you can sort of see that we have this positive region that we talked about over here in the positive x, positive y in the first quadrant, positive in the third quadrant, and it's negative in the second and fourth quadrants. Okay, so that's what this function looks like. Now we can sort of, and you can actually, when you look at a surface plot, you can actually start to see what we might mean by a partial derivative, right? We're sort of walking along this line, one of these lines. So if we're taking a partial derivative with respect to x, what we're doing is we're asking what's the derivative with respect to x as we walk along that line, holding y constant. So to sort of highlight that, let's actually do a plot where we just show what a particular line might look like on this, right? So I'm going to actually hold hold the row constant, right, while allowing the columns to vary. And I'll make a blue line on this that'll be pretty fat, so we can look at what that looks like. So here I'm choosing one particular line, and if I look at this, you know, from the side on, let me see if I can rotate that right. You can see here, this is the line that is changing in x, right? So there would be a negative derivative to that line, and if I look at what that derivative would be, I can also figure out what the sort of corresponding y value is, right? The corresponding y value is -7, and if I ask what's the slope of this line, if I could actually rotate this properly, the slope of that line would turn out to be -7, right? You can sort of see that that is going to be the case. It gets to about 70, -7. It gets to 70 at the point -10. It gets to -70 at the point +10. So it has the appropriate behavior, right? I could also think about what a line looks like for, instead of constant y, constant x. So let's do that, and to do that, we're going to need to hold the columns constant, and make the rows change instead. So they will take the second column, right? And I'll plot this one in red. So this is now a line where we're holding x constant at, I guess, -9, and we're looking at how the value of the function changes as we just change y, right? And so again, you can see that that's a line, right? From the top down, we can see that we're moving along a line where x is constant, where y is changing, or along this line where y is constant as x is changing. And when we look at what the value of the function is, you can actually see that the function is decreasing as y increases, right? It has a slope, and the slope is -9, because the value of x there is -9. So if we do this for a more complicated function, so let's close that plot and let's make a new function. So instead of doing x times y, let's make it be like x squared times y squared, just for the sake of, you know, making something different. So there's x squared times y squared, and we'll again do a surface of that. And I clearly did something stupid. oh, I forgot an elemental operation there. So now if we do this, now we get a different looking surface, right? So this is again the potential here, x-axis here, y-axis here. And again, we can ask the question, what does the function look like if we hold, say, x constant or hold y constant? So let's first hold y constant, and we'll do that with a red line, or I guess hold x constant. Sorry, we're holding x constant, and now you can see this red line, right, is a parabola, right? And so at different points along the y-axis is going to have a different derivative, but it sort of makes sense to ask what's the derivative along that line, right? You can see, and you can see the derivative with respect to the partial derivative at this point with respect to y is 0, right? The partial derivative with respect to y over here is positive, right? The partial derivative with respect to y, sorry, is actually negative because I'm looking at this from the wrong angle. Let's rotate it around, right? So, but you can see at y equals 0, the partial derivative is 0, right? That parabola has 0 slope. When y is negative, the derivative is negative, and it's getting more and more negative as y gets more negative. And when y is positive, the partial derivative with respect to y is positive, right? So the sort of idea here with partial derivatives is that you're basically holding one variable constant and then allowing the other variable to change and asking how does the function, what is the derivative of the function with regard to that variable that you're allowing to change. Okay, and I think that's sort of what I wanted to show you on this. I hope that helps you to visualize what is meant by a partial derivative.